Radiosity method, which actually gained a lot more interest before people started using Monte Carlo methods to solve the global illumination problem. And at least as originally formulated, the radiosity method assumes perfectly diffuse surfaces that reflect equally in all directions. So that means the BRDF is a constant. So for perfectly diffuse surfaces, FR at a point X and two directions, state and psi, it doesn't depend on the directions. It just depends only on X, and we derived before it's the percent of flux reflected divided by pi. So this could still depend on X. Okay, so if that's the case, then we can say the radiance at a position X that's reflected, assuming it's also radiating equal radiance in all directions, so that the emitted radiance also doesn't depend on the directions because it's perfectly diffuse emission too, plus the integral over solid angles of this FR at X, which doesn't depend on angles, and I guess the radiance in. What do I call it? Radiance coming into X by some angle that we don't care about, cosine d omega, which we also, I didn't write the angle there, so I can't write it there either. Now, we can also, I'm going to write in the next formula, I'm going to actually write this, bring this constant outside the integral because it doesn't depend on angles, and I'm going to write it like this. And then I'm just going to change this to an integral over the surfaces. So in that case, it's integral, let's see, where am I? Over surfaces of L at some point y now. That's the radiance leaving the point on the surface corresponding to that direction, Ly times this visibility, which says whether x and y are visible to each other. And we had a geometric factor, x, y, which had this cosine of the incoming angle. Maybe I should write it here. Well, I won't. And also the solid angle cosine divided by r squared for the turning this d omega into area at points y. Right? So this is an equation we had before. I just substituted an FR that depended only on direction, on position, and factored out the integral, and this L also depends only on position if all the surfaces are diffuse. And so what I'm going to do is actually rewrite it as rho of x, the integral over s of L of y, times kernel kxy day, and that kxy has the visibility information, those two cosines in the numerator and the r squared in the denominator, and an extra pi. So if I was going to write out the two cosines, pi, let's say rxy, there's the subscripts. I don't know why I started doing superscripts out of them. This is the distance between x and y, and the two cosine factors were cosine nx with respect to the direction, I guess, xy, and cosine ny with respect to the direction yx. right? So this is the kernel, and then we just have, I forgot my LE here. This was a plus. It's interesting, plus and equals are on the same key on the typewriter, and I always make mistakes that way, but this time I confused them on the board. Okay, so we've just sort of, this is again still this Fredholm integral equation of the second kind, but we've just lumped everything that we had together in the kernel. So this is a sort of a standard form of such an equation with just some arbitrary kernel depending on x and y. Okay, so now let's go back to the definition of radiosity. So by definition, the radiosity leaving a surface is the total flux leaving over all solid angles, integrated over the hemisphere. So B, the radiosity of x, equals the integral, again, over, this is over the hemisphere above x of Lx, I guess we have to have that cosine nx. Why don't I just call it omega for direction? Well, omega, let's call it psi anyway, even though it's d omega psi. So that's the total flux leaving per unit area. And this, again, doesn't depend on the direction. So we can take it outside the integral. And the integral is just the integral of this cosine. Well, okay, I'll just say cosine theta, d omega. And we integrated the cosine over the hemisphere and got pi, right? So this is just Lx times pi. So the radiosity is always the pi times the radiance. So somehow historically this method, which is basically going to be a finite element method, the radiosity is going to divide the surface up into polygons for patches and assume it's piecewise constant on those patches. So if I want to do that with this equation here, I'll just multiply this equation by pi. Right? And that means I can say this will be a radiosity, this will be an emitted radiance. We called that emittance before when we talked about physical units for radiant flux. And this will be multiplied by pi too. So we can say B of x equals, in the book they call it BE of x. I would just call it E of x because we had the emissivity. I mean, normally other texts on radiosity just call it E of x, and that's what I'm going to do most of the period. But anyway, plus the integral omega x of now, it's the integral over all surfaces, I'm sorry, because I'm using the surface form. And now it's just going to be, here's rho of x, b of y times this kernel x, y, dA at y. So all I did was multiply all this terms in this equation by pi, and that changes all the radiances to radiosity. Okay, so now comes the assumption that B of x is piecewise constant, and it's constant on, historically they're called patches. Really they're just pieces of polygons, but they could be pieces of a curved surface. Small enough pieces that if you think of this piecewise constant on them, you get a decent approximation. SI, pieces of part of the total surface area in the scene of area AI. So in practice, once you solve for the radiosity of each patch, you can draw it as a constant. That's sort of like faceted shading. But you could also draw it with Gauss shading. Basically what you'd have to do is, for all the patches that meet at a vertex, average those radiosities to get the vertex radiosities, and then interpolate the vertex radiosities over the patch the way Gauss shading works. And you get a smoothly shaded picture, which would be an approximation to this B of x. And basically, you can pre-compute the radiosity in a scene where nothing is moving, and then move your camera around the scene looking in different directions, and render with real-time hardware what the scene looks like with the global illumination in it. Because you're basically using the historic OpenGL polygon rendering engine for that. Okay, so that means Bx is approximately equal to Bi, a constant on each patch. So that means we can rewrite this equation, Bi for the constant on the patch. Actually, in the book they call it Bi prime. I'll probably stop using the primes pretty soon. It goes Bei, which I'll probably start calling the emissivity of the patch, plus the integral. Well, let me put the rho. Actually, I'm going to assume rho is constant on each patch, too. It doesn't make sense, say, for these walls or floor or, my pants if they weren't so dirty. Constant reflectivity, where the reflectivity of the walls may be different than the reflectivity of the blackboard or the chairs, but certainly that's often true in practice. Okay, so that means I'm going to have a constant rho I here for this rho of x, and now I have integral of the surfaces of B. What do we call this? Well, I can't put it. Let me keep it B of y, and then I'll substitute after I break this surface up into a bunch of different surfaces. So what I want to do is rho I want to take the sum, this integral, as the sum over surfaces j, right, of integrals over Sj, where Sj is one of the other patches in the scene. This whole S is the union of these patches Sj, and now over each Sj I can really write this as Bj prime, another constant times k x y day, and that means I can take that constant out of the integral. Plus rho I times the sum of j. And so what's left of the integral I'm going to call Fij. So this is going to be Fij times Bj prime, where Fij is the integral, well, let's see. I'm missing this one is supposed to be the average radiosity. So I missed a step here. What I want to say is that, let me put it under here, because I think I've gotten things a little messed up here compared to my notes by reading without writing on the board without reading my notes. What we want to describe is Bi is the average radiosity over the patch. So that's the integral over patch Si of Bi of x dAi. Or dAx, I guess. Because it's not really piecewise constant. Basically, if on this right-hand side of this integral I had a piecewise constant function, it still wouldn't be true that the left side of the integral was piecewise constant. Because, even if we had like constant lights on the ceiling, when you're closer to the light, it's going to be brighter than when you're far away. So if I had a vertical thing here, the actual lighting would change. So really what I have to do here is write this piecewise constant piece. If this equation is going to make sense, this is going to be the integral over AI dxi. And if it's the average, I made a mistake here also, because if it's the average, I have to integrate and then divide by the area. So this is actually what I'm going to determine to be my piecewise constant thing. And what that's going to do, the average, if the emissivities are really constant, and that makes sense, light sources, if they have like flat diffusers on them, probably are independent of where you are on the light source. But this one, okay, so now let's see, how does that change it? This is going to be over AI here, and this is going to be, let's see, can I put my integral? Well, if it's a sum of integral sum, it doesn't matter that. This is SI dAx. Sorry for having modified it and make you modify your notes. So now my Fij is going to be 1 over AI, the integral of Si, the integral of Sj of k x y dA y for the inner integral and dA x for the outer integral. And these are called the form factors. Basically, they don't depend on the reflectivity of the scene or the brightness of the light sources. They only depend on the geometry, the way the two surfaces relate, plus any occlusions that happen in between them. They depend on the geometry of the scene, because kxy depends only on the geometry of the scene. And that's why they're called form factors. They basically depend on the form of the arrangement of patches. So, assuming we could calculate them, and that's a topic for maybe the next 2 lectures, then this thing is just a system of linear equations for the bi prime. In fact, we can make it linear equations by writing it in matrix form and then putting all the b's on the right term. So this says b equals e, a column vector of b's equals a column vector of e's, plus this is going to be a diagonal matrix of rows, right? One for each. I mean, basically, you multiply a diagonal matrix by another matrix. You get the new matrix where each diagonal entry is multiplying a whole row of the matrix. And that's what this is doing here, because for all the j things in this column, this row is multiplied by the same row I. So we can make a diagonal matrix of rows and matrix F of the form factors multiplied by this column vector B. And to put all the b's on the left side, we're going to say this is B. Let's see, I'm going to erase this because I want to leave room for what's multiplying it. The identity matrix minus row F multiplied by B equals E. And so in this system of linear equations, B is just the identity minus row F inverse multiplied by E. Or you could use any other method of solving linear equations that maybe was iterative or Gaussian elimination that didn't specifically require you to compute the inverse as part of the solution. So it's just a set of linear equations So the problems in giving a good radiosity method are first figuring out how to divide things into the appropriate patches, fine enough that it'll give you a good approximation, how to compute all the form factors, and how to solve the linear equation. So if you have like 1,000 patches, you have 1,000 by 1,000 matrix there. You know, inverting it would be a big hassle, and it would take time 1,000 cubed. But there are other iterative methods for doing it. And to explain why those iterative methods work, I need some properties of the form factors, and these are the properties in the book. Property 1 is Fij is greater than or equal to 0, right? Because this k thing that we're integrating is, it's way over on that other board, but all the terms are non-negative. And number 2, it says the sum over all j of Fij. That means the sum of the entries in a given row is less than or equal to 1. In fact, it will equal 1 if you're entirely surrounding the scene. You know, no open windows through which you can see outer space that energy can go out of. And the way to realize this is to say this sum of j of Fij is the sum of j of the integral Si integral Sj of, let's see, the cosine was Vxy, sorry, cosine x xy cosine, I'm sorry, nx ny yx pi r x y squared dy. Okay, and then, I'm sorry, day and then dax. So this is the inner integral, and basically this factor, and that factor are what gave us our, and I guess this factor. This is really d omega for the parts of the surface Sj that are actually visible at this x, which is fixed for a given value in the outer integral computation, right? And so what this is if you add them up over all j, you know, we can put this sum inside the integral. This is the integral over Si of the terms that are left. I'm sorry, this is part of it too for the solid angle. This is the visible solid angles of surfaces divided by pi times the cosine nx xy d omega, I'm sorry, dax. And I forgot my 1 over ai in this formula for the form factors, as I've consistently been doing all period because I'm not looking at my notes. And if all the surfaces were visible, this would just be the integral, all the solid angles weighted by the cosine, and that would be pi. If some of the surfaces aren't visible, I mean, if some directions don't hit a surface, just go off in outer space, then this integral, this factor will be less than pi. But in any case, the factor over pi is less than or equal to 1, so we have it's less than or equal to the integral over Si of 1 dAI, which is equal to, this adds up to AI, and so that's 1. So that's this property, and the third property is a reciprocity. AIFIJ equals AJFJI. And the reason is, let me do it on this board because I have this formula here. Let's see. Yeah, I still got my matrix equation there, which is equivalent to this one, so I can erase it. If I multiply this by AI, Fij, that'll cancel this AI here, and I'll get the integral Si integral Sj of Kxy dAy dAx. And the point is, if you look at this formula here, this is symmetric, right? I've got both cosines, and this is just a distance I forgot squared here. Sorry, at least I got it there on the right-hand board. And visibility, if x is visible to y, y is visible to x. So that means this is the same as if you switch the order, right? Since that means this is the same as integral Si integral Sj Kyx dAy dAx. And this is a 2D integral, actually 4D, because each of these are 2 dimensions, but it doesn't matter which you write as the inner integral and which you write as the outer integral. It's just one big, limit of a Riemann sum over samples everywhere. So this is the same as integral Sj integral Si of the same thing. And now this is going to be dAx inside and dAy outside. And that's just for the same reason of putting a j here. That's Aj times Fji, right? Because this integral then becomes a different definition of Fji. So it's not symmetric, but it's symmetric when you get these weightings of Ai and Aj. Okay, so now let's go back to trying to solve this equation. So there's something called a Neumann series, which says that the inverse of 1 minus any matrix equals 1 plus that matrix squared plus that matrix cubed. This infinite series, if that infinite series converges to a matrix. And that's pretty easy to check just algebraically without worrying about the convergence, by just multiplying this thing by 1 minus rho f, 1 minus the matrix, times 1 plus this matrix. And you'll have, I call it 1, it's really I. I times I is I, and now I have a minus rho f times I, which is that, and I have an I times a plus rho f. Then I have a minus rho f times this plus rho f, which is minus rho f squared, and then I have a plus I times this rho f. You can see all these minus terms will cancel the plus terms, and it'll just come out to be the identity. Okay, so that cancellation only makes sense if these series converges, in particular if the magnitude of each term gets smaller and smaller. Then this sort of magical crossing off makes sense. Otherwise, this series doesn't converge. The whole thing doesn't make any sense. So I want to show that in our application, the series does converge. So what I'm supposing is that if you take the maximum of all the rows, right, so whatever that maximum is, rho I is less than or equal to it because it's the maximum of all of them, I'm assuming that maximum is less than 1. And that makes sense because there's no perfectly diffuse reflector. There's no there is no reflector that reflects all of the energy. Some amount is going to be absorbed, even when you're perfectly white shirts. So with that assumption, I claim, let me get to my next page of my notes. That 0 is less than or equal to rho f to the n. Any entry of rho f to the n is less than rho max to the n. It's probably less than or equal to. Right? If I can prove that, then I'll prove this series converges, right? Because every matrix entry of this infinite sum is going to be dominated by the corresponding power of rho, and this is a convergent geometric series. So you have to know a little something about convergent series, which I'm not going to bother to prove, which is that if each term in a series is less than the terms, and they're all non-negative, and they're all less than the terms of a convergent series, then that series also converges. And then this geometric series converges if rho max is less than 1. So let me prove this by induction. So for k equals 1, the claim is that every term of the matrix rho f, the ijth column, is less than or equal to rho max. I'm just putting n equals 1 into this thing. Obviously, they're all non-negative. We just finished saying that the Fij's are non-negative, and the rhos are not going to be negative either. You can't gain energy by shining, how can I say it? A surface reflects something or 0. It doesn't reflect a negative amount. So these things are less than or equal to 1. That's a consequence of being non-negative and adding up to 1. They all have to be less. So these two things imply each Fij is less than or equal to 1, right? Because you couldn't add, if it was bigger than 1 and you added more non-negative things to it, you couldn't get something that was less than or equal to 1. So each of the Fij entries are less than or equal to 1, and let's see. If I guess, right, and I said the way you multiply the rows of this matrix by the capital rho, the Greek rho, you multiply the ROWS of this matrix by one of these RHOs, and you get an element of this matrix here. So it's dominated by that because these numbers are less than or equal to 1. So we got the n equals 1 case. And then assume true for k, show for k plus 1. So basically what I need to look at is rho f to the k plus 1 power, the ijth entry of that. And that is, if I to use the induction hypothesis, I'm going to have to pull off a rho f and then a rho f to the k power and look at the ijth term of that. So now I'm going to have some more inequalities here using those properties on the next board. So what can I do? This equals just the matrix multiplication rule. It's the sum over k of, say, rho I f I k, the ik element across the ith row of the left-hand thing we're multiplying, times the kj element of the other thing we're multiplying. Right, and that's, I don't need the ij element on it now because I've already got I and j in this formula. This is just the formula for matrix multiplication. And now my induction hypothesis says that this part here is less than rho max to the k. Right? Because I'm proving it by induction, and my induction hypothesis assumed it was true for k. And I already proved the base case for k equals 1. And let's see. Because rho I is less than or equal to this maximum, I get this is less than or equal to rho maximum to the k time, because this times that is true, and I'm sorry, this is, boy, I should have, let me make this assume true for n, show it for n plus 1, because k was my ijk formula that I always use for matrix multiplication. Okay, because I had k meaning two different meanings there. Okay, now I'm okay. So now I'm factoring this constant. This was n, and now it's n plus 1, because I've got this particular one is less than or equal to the maximum. And now I have the sum of fik over k. But by property 2 on the other board, that's less than or equal to 1. So that means this has got to be less than or equal to rho max to the n plus 1. And that's what I was trying to prove by induction. Okay, so I have that claim, and that's what I need to show these theories converges. So what happens if we actually apply that formula to it? What that formula is going to say is that the solution, maybe I'll put it over here. I said B equals I minus rho f inverse of E, and that's going to be E plus rho f E plus rho f squared E plus higher order terms. Basically, it says you start with the radiosity solution equals the initial emissivity. And then this is going to compute the one reflection worth of emissivity off of other surfaces. It's like you're tracing your ray to the other surface and then doing direct illumination on that. And this gets 2 bounces of the light from the emission, and so forth. And so you add the direct emission, the first reflection of the emission, the second reflection of the emission, and so on, and you get the answer. So I can write actually an iterative method for solving this equation. Maybe I'll write it here. So let B, the 0th iteration, start off just being the emissivity. And then let B, for the kth iteration, be EI plus this term here using the previous answer. And this matrix of form factors and reflectivities. So if you do that iteration enough times, you are going to get n terms of the series, right? Because this is going to look like EI plus rho f times the next one, which was EI plus rho f. If you substitute again, I guess my dots should be here rather than here. In fact, I'm not even sure my parentheses match. No, they do. So basically, if you multiply out this iterated substitutions, you're going to get exactly the formula I had on the other board. EI plus rho f. That's not EI anymore. This is this. If I'm making column vectors, I've got no i's. This is just the column vector of emissivities plus rho f squared times the column vector of emissivities plus rho f cubed times the column vector of emissivities, and so forth, as I had on the previous board. So this is the emissivity, the first reflected emissivity. Every time you add another term, you get more bounces. And the basic idea is each time you bounce, the fraction of the flux gets absorbed, so this series converges. You can stop after a finite number of terms. So this is called, I forgot the name of it. Whose iteration? Jacobi iteration. And now I'm going to write a piece of code that looks like it implements that. I've got it on my next page here. So for I equals 0, I less than the number of iterations, I'm going to call it capital N. No, N is the number of patches. Because basically the first thing I want to do is make the initial radiosities, which is like my 0 stage there, Bi equals the emissivity, which I'm assuming that's known. It's my right-hand side of my equations. And then for the number of iterations, k less than, say, max iterations. And now I'll just say for each patch, I is the number, n is the number of patches. I'm going to initialize Bi equals, I'm sorry, it should have been brackets now because it's C code. Right, that adds on this term. And then I have to add on the multiplication. So that's for j equals 0, j less than n, plus j, b I plus equals rho I times f I j times bj. So here is this loop, and here is this loop. I guess I didn't need these brackets because it's only a single statement inside my for. So is this implementing this algorithm? There's a subtle difference. This statement says I start with a column vector and then replace the whole column vector by creating a column vector of this equation for the right side of, for this column vector. In other words, it says given this column vector, compute a temporary column vector and assign it to the next iteration. Which means every time I compute an iteration 1 answer, I'm using an iteration 0 right-hand side here for the b's. Whereas here, once I compute the new bi applying this loop for I equals 0, now b of 0 is an updated version. It's not the 0th iteration anymore. It's got the first bounce of the light. And similarly, for every I, it's got, in this first iteration, it's got the first I minus 1 bounces of the light from the I minus 1 previous patches. So this actually is going to converge faster than that one, because parts of the computations doing it at each iteration already are taking advantage of new values. Not to mention, it doesn't have to have a storage for a second column vector, because one entry at a time you're updating it. So this is actually called Gauss-Seidel iteration. And because on average, half of your values that you're using have already been updated. One iteration of Gauss-Seidel is basically worth 1.5 iterations of the Jacobi. And so this is the one that's more commonly used. But basically the argument that it's going to converge still applies. You look at the residuals and they're even better in this one. The residual means how far the error is from the true consistent answer. So that's basically all I wanted to say today. Next time, and probably the time after, we're going to talk about how you actually compute these form factors and what they mean. But they sort of take into account the average visibility and, flux going from one patch to another. So that's it for today.